Okay, welcome everyone. So today we have Brad Leroux from UC Davis. So he will be talking about expansion of random 0-1 polytopes.
Yeah, okay, thanks very much. Yeah, and thanks for inviting me to give the talk. So yeah, the title of it is Expansion of Random 0-1 Polytopes, and we have a recent a paper with the same title. And this is all joint work with Luis Rademacher. So I have this funny little picture here on the first slide that you hopefully see. I'm not sure that pictures are really that helpful for this sort of thing, but I guess you can be the judge of that. Uh, okay. And also, feel free to interrupt me at any time. I probably have plenty of time to get through my slides, so don't worry about interrupting at all. Am I still sounding okay? Is it coming through? Okay, great. Okay, so here's a little just outline of the talk. So I'll give you a little bit of background about polytopes, convex polytopes, and then also the definition of expansion of graphs. And then the focus of the talk is going to be this conjecture from the early 90s due to Milena Mihail and Umesh Vazirani. And that conjecture is about expansion of 0-1 polytopes. So I'll explain that, and also this conjecture has some nice applications, so I'll also go over a few of those. So the main result I'm going to be presenting is essentially the random version of this conjecture that I mentioned. And the proof is fairly simple, so I'll actually probably give you a more or less complete outline of how the proof goes. And then if I have time, I'll mention some possible related problems. One of them has to do with how expansion is related to diameter of graphs. So hopefully that will be interesting to some of you as well. Okay. Okay, so first just the definition of expansion. And I'm going to be talking about edge expansion in particular. There are some other notions of expansion as well. But the basic setup is you have any graph, so V is the vertices, E is the set of edges, and then we look at any subset of the vertices S. So I need to define this notation here, delta of S. So this is just the set of edges that go from S to the complement of S. So they connect a vertex in S to a vertex not in S. So then with this definition, the edge expansion of the graph is the minimum of these ratios, the ratio of the size of delta of S to the size of S. And the minimum ranges over all subsets that are at most half of the vertices. So one way of thinking of edge expansion is sort of a graph will have good edge expansion if it doesn't, or it will have bad edge expansion if it has like a big bottleneck somewhere in the graph. So it's sort of a notion of connectivity. So I also am mainly interested in polytopes though, not just general graphs. So polytopes, here's just my definition of a convex polytope, which is the convex hull of some finite set of points in Euclidean space. And as I mentioned, I'm mainly going to be interested in a specific type of polytope, 0-1 polytopes. So those are just polytopes where all of the vertices are 0-1 vectors. So it's the convex hull of some subset of 0-1 to the d. So now we can also talk about expansion of polytopes. So what we mean by the expansion of a polytope is just the expansion of the graph of the polytope, where the graph of a polytope is simply the graph, which is formed by the vertices are the vertices of the polytope, and the edges of the graph are the edges of the polytope. So it turns this potentially high dimensional polytope just into a structure that we can draw just on the plane. I will also at some point make use of higher dimensional faces of polytopes, but the main interest is in just the vertices and the edges, the structure of that graph. Okay. Okay, so yeah, here's the main kind of motivation for this whole talk, which is this conjecture that I mentioned due to Mihail and Vazirani. So it says that the edge expansion of the graph of any 0, 1 polytope is at least 1. Okay, so this is a pretty surprising conjecture, especially when you think about expansion for arbitrary polytopes other than 0, 1 polytopes, because arbitrary polytopes can have very bad edge expansion properties. So I drew a little example here. I'm sorry. So here's just a three-dimensional polytope, and you can see these two walls formed by the black vertices, and then there are a bunch of red vertices on either side of the wall. So this example makes it clear that arbitrary polytopes can have kind of arbitrarily bad edge expansion properties, whereas this conjecture is saying that if you restrict to 0, 1 polytopes, there's something very special about them, and they always have very good expansion at least 1. Okay, so I also want to mention there's a weaker form of this conjecture. Oh, and also, so yeah, this conjecture is like from the early 90s, I think, is when it first appeared. And I'll get to some more motivation of the conjecture in a second, applications. But there's also this weaker form of the conjecture, which instead of saying that the edge expansion is at least 1, the weaker form just says that it's at least 1 over some polynomial function of the dimension of the polytope. So the reason this conjecture is relevant is because, well, first of all, it might be a lot easier to prove, and also it's kind of good enough for all of the applications of this conjecture. Okay, so before I get to the applications, any questions about the basic setup or the conjecture that I'm motivated by? Okay. Okay, so yeah, the main application of this conjecture is the problem that I've written at the top here: uniform sampling from a set of combinatorial objects. And so the way this comes about, and the reason it's relevant here, is that lots of sets of combinatorial objects can be described by a set of 0, 1 vectors of some fixed size. And if you have a set of 0, 1 vectors of some fixed size, you can think of it as a polytope just by taking the convex hull of those vectors. Then, if you look at the graph of this polytope, it's kind of a standard fact that if the graph has good edge expansion properties, then a random walk on the graph is going to mix rapidly, which means it's going to approach the stationary distribution in, say, a polynomial number of steps. And then this is useful because you can then efficiently sample the vertices of the polytope and thus sample from your set of combinatorial objects. So this description is maybe a little bit vague, so I'll give you, I guess, a slightly more concrete example of how this might happen. So the more specific example is this: the randomized approximation algorithm for counting the bases of a matroid. So what I mean by that is just some algorithm which gives you, say, an approximation for the number of bases of a matroid, say up to a 1 plus epsilon factor, and you want to be able to do this in polynomial time. So the reason uniform sampling is relevant is, in most cases, if you can sample uniformly from a set of combinatorial objects, say, then you can also do you can also design a good randomized approximate counting scheme. But for this application, I'm specifically talking about counting bases of a matroid. So say you have a matroid M, any matroid at all, doesn't matter. So I don't know how familiar everyone is with this, but you can form the matroid base polytope of M. And what that is you just take the 0, 1 vectors, which correspond to bases of the matroid, and then takes the convex hull of them. So this is, of course, a 0, 1 polytope, and it sort of encodes the combinatorics of the matroid in a geometric form. So there's a recent result, really just from 3 or 4 years ago, that proved that the edge expansion of the graph of any matroid base polytope is at least 1. So in other words, they proved this conjecture that I was talking about for matroid base polytopes. So the effect this has is you get a polynomial time algorithm for approximating the number of bases of a matroid. So this is something that we can all appreciate, I guess, because matroids are such ubiquitous things. So this sort of algorithm leads to a bunch of different interesting things, like approximating various statistics about graphs, like the number of forests or the number of connected subgraphs or that sort of thing. And then the other reason it's interesting is this other fact I have down here. So it's been proven, I forget by who, but it turns out that to count the number of bases of an arbitrary matroid exactly is sharp P hard. So it's sort of interesting that there's this simple, efficient algorithm to approximate them, but counting exactly is known to be difficult. Okay.
Is there a particular good property of Metroid-based polytope that is used here?
Actually, not really. So this citation 1, where they prove that the expansion is at least 1, sort of proved that through other methods. They didn't really look at the polytopes explicitly. They design a random walk on the polytope and then get the expansion result sort of as a corollary of that. So the thing I'm going to be talking about is a geometric proof of good expansion, but theirs is more I haven't actually read the proof in detail, but it's not so much about the polytopes. It's more about a combinatorial proof using properties of matroids.
Oh, I see. Yeah, thanks.
Okay, so I think that's all the applications that I wanted to mention. So yeah, I'll just remind you. Well, okay, so here's the conjecture. It's pretty simple. The expansion of the graph of a 0, 1 polytope is at least 1. So I just want to quickly mention previous work on this conjecture. So it's been proved for a number of interesting cases, actually. So there's this paper due to Keibel, where he proved the conjecture for dimension at most 5. Simple 0, 1 polytopes, hypersimplices, stable set polytopes, perfect matching polytopes. And then earlier on, I think it was proved for matching polytopes, order ideal polytopes, independent set polytopes, balanced matroid-based polytopes in another paper. And then as I mentioned before, it was proved more recently for any matroid-based polytope. And I guess this last point is kind of the most interesting one because it leads to the most applications, as I mentioned. But there's still lots of 0, 1 polytopes which are not matroid-based polytopes, of course. So there's still interest in extending these results, of course. Okay. So yeah, as I said, the main result I want to actually present is that random 0, 1 polytopes have good expansion properties. So here's my definition of a random 0, 1 polytope. So of course there's a bunch of different ways to choose random 0, 1 polytopes. I'm just going to tell you one of them. So we call this the balls into bins model. So you have two positive integers. D is the dimension, n is just the number of samples that you're choosing. And you're going to choose n points independently and uniformly from 0, 1 to the d. So this is going to be then your set of vertices, and you form the polytope just by taking the convex hull. So there's a couple other models that we also consider, but they're all somewhat similar. So this is maybe the one to keep in mind. Okay, so here's the statement of the main theorem that I'm going to sketch the proof of this theorem. So it says we have a random 0, 1 polytope distributed according to either the balls into bins model that I mentioned before, binomial model, or the uniform model, and those are just two other similar models. Then we prove that the edge expansion of the graph of this polytope is at least 1 over 12d with high probability. So this does not match the original form of the conjecture, which is that the expansion is at least 1, but it's still 1 over a polynomial. So it's still good enough for applications.
Can you show the definition of the random polytope again? There was two parameters, right? The d and n.
Yes. Yeah, d is the, yeah.
But in the next theorem, you don't have n, so
yeah, so it's for any n.
Oh, so n is fixed?
N is fixed, yeah. So I guess what this theorem is saying is choose any d and any fixed n, then the expansion is 1 over 12d with high probability.
But for high probability, you mean n tends to infinity, right?
Actually, no, I mean d tends to infinity.
D tends to infinity, okay.
Yeah. So yeah, more specifically what this is saying is the probability is yeah, so the probability that the edge expansion is at least 1 over 12d is some function of d which tends to 1 as d tends to infinity.
Maybe you want to take n as a function of d as well?
Well, yes, n is a function of d. I guess it doesn't make much sense to say fix n and let d go to infinity. N should be growing with d. But the point is that the probability is independent of n. It only depends on d. Does that answer your question, or is there?
Yep.
Okay. Okay. And actually, yeah, I appreciate that question because this is something we were planning to kind of clarify in our paper. Yeah. But I'll also clarify that a little bit later when I'm talking about the proof. Okay. So before I start outlining the proof, I'm just going to give you some basic facts about polytopes. So maybe this is familiar, but if you don't think about polytopes much, I'll remind you. So a face of a polytope, P, and I'm going to use the notation F for the face. It's just any set of this form, the set of solutions to some affine equality that is satisfied by all points in the polytope. So of course the vertices are the 0-dimensional faces, edges are 1-dimensional faces, and so on from there. So proper faces, those are just faces that are not empty or the entire polytope. And then I have this notation, V of P is the set of vertices of the polytope, and then E of P is the set of edges. And then, okay, so besides those basic definitions, the only fact, like geometric fact, that I'm going to use in the proof about polytopes is this fact I have stated here. So P in RD is a d-dimensional polytope. Then for any vertex of P, the set of edges incident to V cannot be contained in a hyperplane. So if you think about polytopes, this is probably pretty obvious. And the proof is also pretty simple. But hopefully you can see why this fact is useful for us to prove expansion properties, because we're going to want to prove that there's lots of edges going out of a certain subset of vertices. So this fact is going to give us lots of edges. Okay, any questions about these, the background facts? Okay. Okay, so the main ingredient in proving the theorem about random 0-1 polytopes is this lemma that I'm calling the projection lemma. So this lemma actually doesn't have anything to do with randomness. It's just a statement about arbitrary 0-1 polytopes. So here's the statement. So take any 0-1 polytope and assume you have k coordinates. You can think of them as the first k coordinates. And if you take the orthogonal projection to those k coordinates, then two nice things happen. So the first nice thing is this bullet point here. So the projection of P is equal to CK. And CK is just my notation for the k-dimensional cube in RK. So the projection is the entire cube in the projected space. And then the second fact here, or the second condition, is that for every vertex of the k cube, the cardinality of this set here is at most C. So pi k inverse of V intersect V of P, that's just the set of vertices of P which are projected to V. So for any vertex of the cube, not too many vertices of P are projected to that vertex. At most C of them are. And then if this is true, the edge expansion of the graph of P is at least 1/2C. Okay, so no randomness yet, just a projection condition. Okay, so I'm gonna try and go through most of the proof of this lemma because it's pretty simple. Okay, so to prove the expansion is at least 1/2C, we need to show that for every subset of vertices, there's lots of edges going out of it. So I'm going to say R is any subset of at most half the vertices, and then B is the complement. So I'm going to think about R as the red vertices, and B is the blue vertices. Then I have this definition here, bichromatic. So a vertex of the k cube, remember we're projecting to RK where the k cube lives. So a vertex of that cube is bichromatic if there's a blue vertex that projects to it and there's a red vertex that projects to it. Okay. Otherwise, it's monochromatic. So monochromatic vertices are ones where all the vertices that project to it are either red or they're all blue. Okay, so this is the picture that I had on the first slide. So here k is equal to 3. And you can see that we cover the cube by projected vertices. That's the first condition. And then there are some monochromatic vertices and some bichromatic vertices. So from here, there's only two cases. So first case, there's lots of bichromatic vertices. And then the second case is there are lots of monochromatic red vertices. Okay. And I'll explain now what I mean by many vertices. So we know that the size of the projection of R is at least R of the size of R over C. And this is just because of the second condition. No vertex of the cube gets more than C vertices. So using this condition, we know that either there's at least R over 2C bichromatic vertices, or there's going to be at least R over 2C monochromatic red vertices. Okay, any questions about this case analysis or? Okay. Okay, so the first case is the easier one. Now you'll see what kind of happens in this proof. So the first case is there's at least R over 2C bichromatic vertices. So what we're going to do now is we're just going to consider the inverse image of each bichromatic vertex. And this inverse image is a face of P, because we're considering the projection as from P to the cube. So the inverse image of each of these vertices is a face of P. And so the reason it's a face, I guess, is because V is a face of the k-dimensional cube. So V has some supporting hyperplane in the projected space. Then pi inverse of V also has some supporting hyperplane, just the inverse image of that supporting hyperplane. So it's a face, and because V is bichromatic, that face contains red vertices and blue vertices. Now we just have to use a simple fact about polytopes. Graphs of polytopes are connected. So if we consider pi inverse of V, the face, as a polytope itself, then the graph of that polytope is connected. So there must be an edge in the face that connects a red vertex to a blue vertex. Otherwise, red and blue would be a contradiction to connectedness. So we found all the edges we need. We found R over 2C edges going from R to B, and this is all that we needed to do. Okay.
Could you explain about the last line? Why do we, so yes, there is an edge that connects a red vertex and a blue vertex. So why does it imply that we have that many edges?
Oh, because, so for,
right.
There's,
No, I actually got it.
Oh, you saw it? Okay. Great. Yeah, it's just the number of, every I'll just say it anyway. Yeah. Every bichromatic vertex projects to it, or
yeah, and every bichromatic vertex corresponds to distinct
yeah, yeah. Uniqueness is just from the projection. Yes, yeah. Okay, so hopefully this makes sense. I think it seems like it does to everyone. So yeah, we've used only very basic facts about polytopes. The fact that graphs of polytopes are connected, I think that's known as Belinsky's theorem. They're actually deconnected, but it's not a super deep theorem. Okay, so the second case is slightly more complicated. There's at least R over 2C monochromatic red vertices. So I'm going to call those monochromatic vertices, the red ones, M. Now I'm going to use a slightly more sophisticated fact. This fact is that the edge expansion of the cube is 1. So this is also a well-known fact. It's sometimes known as like a discrete isoparametric inequality, that the expansion of the cube is 1. But anyway, this fact tells us that there must be at least size of M edges which go from a vertex in M to a vertex outside of M. And remember, M is a subset of vertices of the cube, the K cube. So there's, size of M edges, and size of M is at least R over 2C. So I'm going to use this notation capital E for the set of edges. So I'm actually now going to use these edges, which are edges of the K cube, to find edges that are actually edges of the original polytope. So the way that works is this claim here. So for every edge that I found in E, again, I consider the inverse image of E, and it's going to turn out to be true that that inverse image, which is a face of P, must contain an edge that connects a red vertex to a blue vertex in P. Okay, so that's not entirely obvious, but it's not hard to prove. So I'm going to prove it on this next slide here. So here I just rewrote the claim from the previous slide. So we're going to say the inverse image of all these edges contains good edges that we want. So here's the proof of this claim. So we know that each edge is just the convex hull of two vertices, U and V, where U is in M, it's monochromatic red, and V is not in M. Okay, this was just the definition of E. So then again, we consider the inverse image of V. It's a face of P, and it has two proper faces, which are the inverse image of each of these two vertices, U and V. And remember, say pi inverse of E could just be an edge of P, but it could also be a higher dimensional face. We don't know. And the same is true for pi inverse of U. That might just be a vertex, but it could also be a face of another dimension. Okay, so from here, we know that V is in the complement of M. So this implies that the inverse image contains a blue vertex, because otherwise V would be monochromatic red. Now I'm going to use the fact I mentioned earlier, which says that for a polytope and a vertex, the set of edges incident to that vertex cannot be contained in a hyperplane. So that means the set of edges incident to V cannot be contained in pi inverse of V. There must be an edge that goes out of pi inverse of V. So it must go to pi inverse of U. Then pi inverse of U only has red vertices. So this edge gives us what we want. It gives us an edge that connects red vertex to a blue vertex. Okay, so that's essentially the end, but are there any questions about the details of this proof or any comments?
Sorry. Could you explain why M is not too large? There's at most half of the vertices of the cube.
Oh, that's a very good question. I was kind of trying to I didn't say why you can assume that. That's like a minor technical thing, which
it probably follows from that your red vertices were at most half of your set of red. Sorry.
Well, so based on what I've said, it doesn't follow a bit from what I said, but we can assume that because otherwise we could consider the monochromatic blue vertices. It's
But so you have the distinction. You either get lots of monochromatic or lots of so you can't really choose which monochromatic.
Mm-hmm. Yeah. So okay. So let me go back. So I think I need to go back to explain. So
it's okay. You don't.
Oh no, no, it's okay. I can do it quickly. Okay, so I think the thing that you need to do is assume, so you know that either the monochromatic red vertices are less than 2 to the k minus 1, or the monochromatic blue vertices are less than 2 to the k minus 1. So if the red ones are less than that, then we do the proof with the red for the red ones. If the blue ones are less than that, then we do it with the blue ones. Does that make sense?
Yes.
Okay. So yeah, it's a minor technical thing, but you're right, a very important point, because otherwise we would not be able to use that the edge expansion of the cube is 1. So yes, very good question, I think. Okay, any other questions? Okay, so that's the proof of the projection lemma that I mentioned earlier. So from here, it's very easy to complete the proof of the theorem. So here I just rewrote the lemma and the theorem. So all that's left to do is to show that random 0, 1 polytopes satisfy these two conditions with high probability when C is equal to like about 60 or 60, I guess is what it is. And this is, I guess, what part of where your question about n going to infinity or d going to infinity comes up, because the value of k that we choose for the projection when we're doing this proof actually depends on both n and d. So if n is very large, then we're not going to project very much. K is going to be close to d. But if n is very small, we're going to have to project very far down. It's going to be much smaller. But it doesn't affect the probability bound. The probability bound still only depends on d. Okay, so, and I didn't plan to talk about the rest of the proof, because the proof that these two conditions are satisfied is just very basic probability. If you've heard of like the coupon collector problem or the balls into bins theorem, the proof is essentially that sort of thing. It's basically just saying that if n is large enough and we choose k appropriately, then the first condition will hold. The projection will be the entire cube because n is sufficiently large compared to k. So if we choose enough vertices, we're going to cover the entire cube. Then the second condition is just if the vertices are chosen randomly, they'll be more or less well distributed among the vertices of the cube. So no vertex will have too many, most likely. Okay. Okay, so I guess that's the main result that I wanted to present. But are there any questions about this theorem or the proof before I move on to related questions? Okay. Oh, okay. I guess one more thing I want to say is so I mentioned some applications of this of the original conjecture of Mihail and Vazirani. So for random 0, 1 polytopes, there isn't really any application because generally for this sort of thing, we need to know stuff about very specific types of 0, 1 polytopes in order to say anything useful. So our proof of that random 0, 1 polytopes have good expansion maybe should just be seen as some evidence for one of these conjectures that it might be true. And I should also mention there's lots of other questions you could ask about the structure of 0, 1 polytopes or random 0, 1 polytopes, and there's this a survey Ziegler which kind of outlines those, and yeah, this kind of gives you the impression that 0, 1 polytopes can be very complicated, even though they in some ways seem simple. Okay, so I also want to mention some other related questions. And this mainly has to do with, yeah, what I have written up at the top of this slide. So expansion for other families of polytopes. So as I mentioned, I give you this example of a polytope that has very bad expansion. There are these two walls that separate all the vertices from all the others.
Brett, your slide didn't change, it seems.
Oh.
We're still not completing the proof.
Oh. Oh, I see. Yes, I think I pressed pause accidentally. Thanks. Okay, so you can see it now, right?
Yes.
Okay. Yeah, so expansion for other families of polytopes. So polytopes in general have bad expansion, right? As I gave you that example with the two walls. But there actually are some other families that have good expansion. And well, maybe I only know of one family, but it's an interesting example. So here it is. There's this theorem due to Collai from 1991, and he proved that the vertex expansion of dual to neighborly d-dimensional polytopes with n facets is lower bounded by 1 over n to the fourth, or on the order of 1 over n to the fourth. And I guess, so I didn't define vertex expansion, but vertex expansion is actually a lower bound on edge expansion. So you can, if you prefer, you can replace vertex by edge in this theorem. And then I should also explain dual to neighborly d polytopes. So neighborly polytopes are ones which, with a given number of vertices, have the maximum number of facets over any d-dimensional polytopes with a given number of vertices. So they're very important. They're a very important class of polytopes. So it's interesting that he was able to prove that they have good expansion properties. And then I guess the main reason why this theorem is interesting, at least to me, is this general fact I wrote here. So if you have a lower bound on the expansion of a graph, in general, it's easy to get a good upper bound on the diameter of the graph, where the diameter of a graph is just the maximum number of steps you have to take to get from one vertex to another vertex. So as a corollary of this theorem above, you immediately get a very good diameter bound for these polytopes. The diameter is, well, it's polynomial in D and N, which is good. So I guess this is interesting because then it gets us into the territory of the Hirsch conjecture, or the polynomial Hirsch conjecture, which asks for a polynomial upper bound on the diameter of polytopes, which is very important because it's sort of the way that we hope to understand why the simplex method for linear programming works so well. But this is also a very limited class of polytopes. Dual to neighborly polytopes are very special. So it's not necessarily going to prove anything about diameter for general polytopes, but there is maybe some hope that it could prove something for random polytopes. So there's this other conjecture from the same paper of Collai, which says that the vertex expansion of a random simple D polytope with n facets is on the order of 1 over n minus d. So the reason this conjecture is interesting is if you prove this conjecture, as I mentioned before, a good bound on expansion gives you a good bound on diameter. So this conjecture would resolve the random version of the polynomial Hirsch conjecture, where again, the polynomial Hirsch conjecture asks for a polynomial up on the diameter of a simple D polytope with n facets. And then the random version asks for the same thing, except for random polytopes. So I guess I also want to explain what is meant by a random simple polytope. So it could mean a lot of different things, but one option is, say, to choose Gaussian hyperplanes, maybe tangent to the sphere, or you could just choose Gaussian hyperplanes with a Gaussian distance to the origin, and then just take the polytope that's formed by the intersection of half spaces. So this is a very interesting class of random polytopes, which is very different from 0-1 polytopes because 0-1 polytopes have this rigid structure where all the vertices are just a subset of the vertices of the cube. But these random Gaussian polytopes sort of, the vertices and the facets can be anything if they're just distributed according to some continuous distribution. So I think this conjecture is interesting, and sort of interesting that it hasn't, I guess no one who works on the diameter problem for polytopes really thinks about expansion. And I think the reason for that is maybe people think this conjecture I've stated here is probably even harder than proving a similar statement about diameter. But I think it's still an interesting connection with another problem. Okay. Okay, so I think that's all I had to talk about. I just have some references here. So this first one is that recent paper I mentioned about Metroid-based polytopes. And then these other ones are just older work on expansion of 0-1 polytopes. So if there are any questions, let me know. Otherwise, thanks very much.